Hi everyone. In last session, that is part 4, we have discussed about Oppo principle and N plus L rule. Based on N plus L rule, we have decided energies of different orbitals. Briefly, I will explain. As per N plus L rule, if an orbital has more N plus L value, that is with more energy. N plus L value of any orbital is less, then its energy also less in comparison. If both orbitals are given, among those two orbitals for which more n plus L value is there, for that particular orbital energy will be more. Another orbital with less n plus L value is with less energy only. In case two orbitals have same n plus L value, in case two orbitals have same n plus L value, then we have to consider n value among those two. More n value, more energetic, less n value, less energetic. These things in last class we have discussed. So as per these two rules, n plus L rule is one of the sub rule of Oppo principle. So Oppo principle and n plus L, among by using these two, we can prepare one order of energies of various orbitals. Order of energies of different orbitals, increasing order we can write. For this, we can take first diagram, which is nothing but Euler's diagram. See here, I am writing Euler's diagram here. Euler's diagram. For this basis, in previous classes we have discussed about number of orbitals present in given shell equal to its shell number. So, for example, if it is n value, here I am writing n value. If n value is 1, in this only one s orbital is present. See here, for this L value is 0. Then here I am writing L value is 1. Next L value is 2. L value is 3. Like this 3 vertical lines I am taking, different horizontal rows I am taking. See here n value, here 1s, here n value it is 2. Here we have 2s orbital when L equal to 0 and 2p orbital if L equal to 1. Here it is L equal to 2 means it is d orbital. D orbital is not present in second shell. So that here I am not writing anything. If it is third, 3s, then here 3p. Here we can write 3d. Here no f orbital because L equal to 0 means s orbital. L equal to 1 p orbitals. L equal to 2 means d orbitals. L equal to 3 means f orbital. F orbital is from fourth shell. If it is 4s orbital, then 4p orbital, then 4d orbital, then 4f orbital, like this. In this way we have to check. If it is fifth shell, 5s, then 5p, then 5d, then 5f, and 5g also there. But already in last sessions we have discussed for writing electron configuration for 118 elements which are there in the periodic table, here up to f orbital is enough. No need to write g orbital. If you write g orbital also there is no electron, it becomes empty only. So that empty orbitals have no importance, so that I am not writing. Then sixth shell if you take, here 6s, then 6p, then here 6d, 6f also not required, because if you write 6f f orbital also there is no use, because if you write electron configuration in 6f orbital there will not be any electron. Electrons are not present in f orbital of sixth shell, so that I am not writing. But here you can write 6f, 6g, 6h, like that. Then 7th shell, 7s, 7p, 7d I am not writing, 7f I am not writing, 7g I am not writing, because for writing electron configuration again for 118 elements there is a requirement of only p orbital from 7th shell. Here 4th shell if you take, up to 4f orbital is required. 5th shell 5f orbital is required. In 5th shell 5g is not required. In 6th shell 5g and 5f, 5h, all these orbitals are not required, because only if you count here, see each and every orbital you know how many electrons it can accommodate. S orbital can accommodate, only 2 electrons, S orbital if you take, it has only one box, it can accommodate only 2 electrons. If it is p orbital, it can accommodate a maximum of how many electrons? 1, 2, 3, 4, 5, 6. So S maximum is 2, P maximum is 6. D maximum in this we have 5 suborbitals like this. Each orbital can accommodate 2 electrons with opposite spin. Therefore, here maximum of electrons are 10. F orbital, if you take here, we have how many boxes? 7 boxes. 1, 2, 3, 4, 5, 6, 7. Here 1, 2, 3, 4, 5, 6, 7. Like that, if you write anti-clockwise electrons, here we can get 14. So if you write here like this 2, 2, 2, 2, 2, like that 7 twos. How many? Here only 14 electrons. Just a rough idea I am giving. Here p orbital 1, 2, 3, 4, 5, 6. 6 into 6. How much it is? 36. 36 electrons. Then D 1, 2, 3, 4. 4 into 10, 40. 40 electrons here. Here 14, 14. How much it is? 28 electrons. If I add all these 14 plus 36 plus 40 plus 28, how much it is? I think it is 118 you can get. So one for writing 118 electron configuration, we need this many orbitals. How many orbitals are there? Total 19 orbitals. 19 orbitals are enough to write electron configurations of all the elements which are present in our periodic table. How many orbitals? 19. See here 1, 2, 3, 4, 5, 6, 7. 7 s orbitals. Then 1, 2, 3, 4, 5, 6. 6 p orbitals. 7 plus 6, 13. 13 here 4. 17. 17 plus 2, 19. Total 19 orbitals are enough to write electron configuration for 118 elements which are present in our periodic table. Till now, how many are discovered for writing that many electron configuration of that many elements? This is enough. Okay. Here now, as per n plus L rule, as per n plus L rule, which orbital has less energy, which orbital has more energy? Now we have to decide. See, 1s. See here n value 1 and s value 0. These two you can add. N and L. N plus L. Euler's diagram depends on n plus L rule. So here n value is 1, L value is 0. So 1 plus 0, 1 only. Here 2s orbital, 2 plus 0, 2. 2p orbital, 2 plus 1, 3. 3s orbital, 3 plus 0. Here 3 plus 1. For this 3 plus 2. 4f if you take 4 plus 3. Like that if you take energies of different orbitals you can get. Low n plus L value, low energy. High n plus L value, high energy. In case both orbitals have same n plus L value, we have to consider only n value. More n value, more energy. Less n value, less energy. So from this we can write like this. First electron enters into this orbital. After completely filling this orbital with 2 electrons, next electron enters into 2s orbital. Then 2s, 2p, 3s if you take. Otherwise 2p, 3s if you take. Here 3 plus 0, 3. 2 plus 1, 3. These two cross orbitals will have same n plus L value. But among these two, n value of 3s orbital is more. So that 3s orbital has more energy than 2p orbital. So at first, after filling 2s orbital, electron will move to 2p orbital. After filling completely it with 6 electrons, then electrons enters into 3s orbital. Then next, after filling 3s orbital, we have to consider 3p, 3d, 4s. But if you take 3p orbital and 4s orbital, among these two, which is having more energy? 4s. Even though both are having same n plus L value. 3p means 3 plus 1, 4. 4s means 4 plus 0, 4. So both are having same n plus value. But 3p orbital has less n value. So that first electron enters into 3p because it is less energetic. Then similarly, here also we can take 3D first, then 4p, then 5s. All these cross orbitals have same n plus L value again. 3D, 3 plus 2, 5, 4p, 4 plus 1, 5, 5s, 5 plus 0, 5. But 5s orbital has more n value. So that it will take electrons lastly among these three. First, 3D orbital will take electrons. Then similarly, 5D, 4D, 5p, 6s. Afterwards, once you see, like these electrons will enter into different orbitals. This is a Euler's diagram. This is Euler's diagram. See, this is the first orbital, 1s, then 2s, 2p, 3s, 3p, 4s, then 3D, 4p, 5s, then 4D, 5p, 6s, then 4f, 5D, 6p, 7s, then 5s, 6d, 7p. This is the Euler's diagram. By using this, we can write one order first. We have to remember that order. Then after how to write electron configuration for different elements we will discuss. See here, I am writing order of energies. 1s orbital I am writing first. 1s orbital has less energy than remaining all. 2s. Then it is less energy than 2p. Then 3s. Then 3p. 3s. Then 3p. Then 4s. Then 4 after 4s 3d. After 3d 4p. Then after 4p 5s. Then after 4d. Then 5p. Then 6s. Then 4f. After 4f 5d. Here I am writing. Up to 6s here I am writing. Up to 6p, 5p here. Then here I am extending. After 5p. Then 6s. 6s orbital has less energy than 4f. 4f, then 5d, then 6p, then 7s. After 7s, 5f, then after 6d, then after 7p. Then you can count here. How many orbitals are present here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 orbitals are enough to write electron configuration for 118 elements, otherwise 118 electrons. One element is nothing but one electron. Second element means it contains 2 electrons. 118th element means it contains 118 electrons. So to write electron configuration for 118 elements, this many orbitals are enough. Now I am giving one example. Before that, how to write, what is the method? What is the method of writing electron configuration? So here for writing electron configuration we have this method, NLX method. NLX, where N is nothing but shell. Shell is nothing but like this, 5, 4, here 6, 7. This is nothing but normal whole numbers 1, 2, 3 like that. L is nothing but what? L is nothing but subshell. It is a subshell. Subshell means S orbital or P orbital, D or F. X is nothing but number of electrons. Number of electrons means S2, P6, D10, F14 as per the requirement. Maybe it may not completely fill. Maybe sometimes S orbital may contain 1 electron. Sometimes P orbital may contain 3 electrons or 4 electrons, not complete. It depends on number of electrons present in that particular element, the given element. So this is a NLX method. NLX method for writing electron configuration. We have box configuration also. We are having box configuration also. So here I am giving one example, that is gallium. For gallium, how to write electron configuration from this? By using This is how to write electron configuration for gallium. See here, gallium atomic number first of all you should know. Directly in examination they will not give atomic number. See first session or first part of this Fundas chemistry or second session if you observe there are given clear information about atomic number, then atomic mass number, otherwise atomic weight, their particular element name also are given, particular element name also are given. From that we can write atomic number. Otherwise we have to remember, we have to practice minimum up to 30 in this level, minimum up to 30 atomic numbers with their atomic weights you have to remember. See one more time here I am writing order of energies. First 1s, then 2s, 2p, 3s, 3p, then 4s, 3d, 4p, 5s, 4d, 5p, then 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So these are the different orbitals with their increasing order of energy. Increasing order of energy, and not given here less than sign or greater than sign. This is increasing order from left to right. 7p orbital has more and more energetic than 1s orbital or remaining all other orbitals. So here what example I am giving, gallium I am taking. Gallium atomic number is 31. Always we have to write atomic number at the bottom. Up to 30 elements are given. In previous sessions, see in that video you can get all atomic numbers with their atomic weight. So for 31, what is the atomic number? Atomic number is nothing but number of electrons. So here in gallium, number of electrons are equal to 31. Now we have to write 31 electron configuration for 31 electrons. Now what you have to do? These 31 electrons we have to throw into this order. That means first among these 31 electrons, first electron enter into which orbital? Among all available orbitals, all are available orbitals. Among all these available orbitals, because already I told, in any given atom, number of shells or number of orbits or number of energy levels are equal to infinity. Then number of subshells are also equal to infinity. But among infinity, this many orbitals are enough for writing all elements electron configuration. So these are the available orbitals. Among these available orbitals, first electron enters into which one? This one, as per Auber principle. Second electron also enter into this, because there is a accommodation for 2 electron. For s orbital, how many electrons it can be accommodated? 2 electrons, maximum of 2 electrons. P orbital, it can accommodate a maximum of 6 electrons. D orbital, it can accommodate a maximum of 10 electrons. F orbital, it can accommodate a maximum of 14 electrons. Right? So 31 electrons are there. For 31 electrons, first 2 electrons enters into 1s. Here I am writing electron configuration, EC. EC means electron configuration. 1s, 2. Then number of electrons remained are now 29. 29, next 2 electrons enters into 2s. 2s2. Then after 2p p orbital, it can accommodate a maximum of 6 electrons. Up to here 10 electrons over. So now remaining electrons are 21. Next electron enters into 3s. 3s2. Then next 3p 6. I think up to here 18. 2 plus 2 4 plus 6 8. 8 plus 4 plus 6 10. 10 plus 2 12. 12 plus 6 18. So up to here it is completed. Then 4s. 4s2. Then after 3d. 3d 10. Then up to 3d 10. How many electrons are completed? 2 plus 2 4 6 10 plus 2 12 plus 6 18 plus 2 20 plus 10 20 plus 10, it is 30. 1 electron. That 1 electron enters into 4p. 4p1. Even though p orbital can accommodate a maximum of 6 electrons, but here only 1 electron is remained after filling 3d orbital. Only 1 electron is remained. That electron enters into 4p orbital. So this is the electron configuration. So here this is NLX method. 1s2. NLX, 2s2, NLX, 2 electrons. X is nothing but a number of electrons. L is nothing but orbital. N is nothing but shell number or orbit number. For the same, we can write box form also. Before writing box form, we can write it in this is the orbital wise configuration or NLX method. Then here shell wise configuration I am writing. Shell wise. Shell wise means in first shell only 2 electrons. In second shell, this one, comma 8 electrons, 2 plus 6. In third shell, 3s, 3p, 3d. In third shell, how many electrons are present? 2, 6, 10, 18. 18 electrons are present. Then in fourth shell, 4p, 4s, then 3. This is the shell wise configuration. Shell wise means what? For example, this is the nucleus. This is the first shell. First shell contain only 2 electrons, that is 1s2. Second shell, 2s2, 2p6. Third shell, 3s2, 3p6, 3d10. Fourth shell, 4s2, 4p1. So total here number of electrons are 2. Here 8, here 18, here 3. So this is the shell wise configuration. Then we have one more configuration, that is box wise configuration. Box wise. Box wise means here S orbital contain only one box, 1s2, then 2s2, then 2p, like this, then 2s, 2p, then 3s, then 3p, 3p, 3 boxes, then 4s, then 3d, 1, 2, 3, 4, 5, then 4p, here I am writing 4p. Now you have to write electrons. Here 2 electrons, here 2 electrons, but while writing electrons, here 1, 2, 3, 4, 5, 6, in this way you have to write. Here up to here 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, here 24, 25, 26, 27, 28, 29, 30. Here only one. Lies your right electron configuration in box wise. So this electron configuration is writing electron configuration is very important for understanding further concepts. If you don't know about atomic number, if you don't know about writing electron configuration in shell wise, in normal orbital wise, NLX method, otherwise shell wise or box wise configuration, if you don't know to write means it is somewhat difficult to understand further concepts in particularly chemical bonding or periodic table. Even organic chemistry also it is base. So first of all you should know how to write electron configuration for given element. From this only all the concepts are linked to electron configuration. It is a base. It is a base for understanding many concepts. Without electron configuration it is not at all possible for writing formulas. For writing formulas, for getting compounds. So this is a very important basic thing. From this only we have to take valency, combining capacity, how one element can combine with how many other elements. All these things based on this only. So this is one example. Then see in this in outer shell how many electrons are present? How many outer electrons are present? How many core electrons are present? Already in previous class again, valence shell, core shell. Valence shell means what? Is nothing but last shell or ultimate shell. Last before shell is nothing but n minus 1 shell, penultimate shell. Before penultimate shell we have n minus 2 shell, that is anti-penultimate shell. Ultimate shell means last shell, otherwise valence shell. Remaining all are n minus 1, n minus 2, n minus 3, all these are considered core orbitals, core shells. So here my question is how many valence electrons are present? Valence electrons here. Valence shell means which one? Last shell is fourth shell. First shell, second shell, third shell, fourth shell. First shell otherwise called as K shell. Second shell L, M, N. So last shell is which shell? Fourth shell. So that last shell electrons are valence electrons, or we can write for this configuration particularly fourth shell electrons. Fourth shell electrons are equal to 3. Generally, in any chemical bond or any chemical reaction, Last shell electrons are participated, depends on condition. Then core electrons. Core electrons are nothing but here inner shells other than fourth shell. Inner shell electrons. Inner shell electrons are how many? Other than this, how many? 2 plus 8 plus 18. It is 28. 28 electrons are present. So you should know these things. After writing electron configuration, what you have to observe? How many electrons are present in last shell or ultimate shell or valence shell, and how many electrons are present in inner shells, otherwise core electrons. So here as gallium electron configuration, valence electrons are equal to 3. Core electrons are equal to 28. These things we should know. From this concept only, we can get some more information or some more basics related to periodic table. Periodic table, long form of periodic table. Different periodic tables we have. Previously, some periodic tables they they gave some periodic tables based on atomic weight. But here it is not depends on atomic weight. Here atomic number concept it is. Otherwise, electron configuration. Based on electron configuration, as per this Euler's diagram or Aufbau principle, we have long form of periodic table. So I'll give some basic information related to periodic table, how to construct periodic table. Then in periodic table, how we can get 7 periods and 18 groups. All those things we'll discuss. How many blocks are there in particularly periodic table, S block, P block, D block, and F block. All these things I think we read in your 10th level or 9th level. Okay, here periodic table, how we can construct this periodic table, we'll discuss now. Okay, here basic information in next sessions we'll discuss how to construct, but what is the information related to periodic table we'll discuss now. I'll give clear picture about periodic table by drawing on board in next session, but for that what is the basic information we'll discuss now. Basic information is periodic table was constructed by, here this you should know, periodic table was constructed by Niels Bohr, remember, scientist name writing, Niels Bohr. What is the basis? On the basis of, here I am writing, on the basis of Bohr principle. What is the basis of Bohr? Bohr principle. Bohr principle, or we can write N plus L rule, and also Euler's diagram. Euler's diagram. See, as per Euler's diagram, you got this order now. So here actually, next point here is the basis is Bohr principle. On the basis of Bohr principle, we got this order. So for this, after knowing this order, how to use this order while constructing periodic table, we should know. As per this Niels Bohr, here every period starts with s orbital. Every period starts with s orbital and end with p orbital. And with the p orbital, except first period. First period starts and ends. Starts and end with same. And with s orbital only. This is the exceptional case that you have to remember. So every period starts with s orbital, end with p orbital. Like this we see here I am giving. It starts with first, this is the first period. It starts with s orbital, end with s orbital only. Then here like this I'm writing. Start with s orbital, end with p orbital. Second period. Third period, start with s orbital, end with p orbital. Now fourth period, start with s orbital, end with p orbital. Here, this is up to here fourth. Fifth period, start with s orbital, end with p orbital again. Sixth period, start with s orbital, end with p orbital. See, you can observe here only one orbital is there. Here two orbitals are there, 2s 2p, 3s 3p, 4s 3d 4p. Number of electrons are increasing here. Here 5s 4d 5p. Here 5s 4f 5d 6p. Then last period. So in this way we can expect 7 periods in our periodic table. How many periods? 7 periods in our periodic table. This is the first period. Then here I am taking some space here. One more time I will write. Here this is the first period. Period number I am writing. P. P is nothing but period. Remember. First period, this is the second period, third period, fourth period, fifth period, sixth period, then seventh period. Right. Then already just I given no every as per who constructed is Niels Bohr. This periodic table was constructed by Niels Bohr. Depends on this diagram. So every period starts with s orbital and end with p orbital. End with p orbital except first period. Except first period, which is starts and ends with s orbital only. But this was constructed by this. All these things are given by Bohr. This is the period. Then here number of electrons I am writing. Number of electrons. See how many electrons are present here? Only one is. So only 2 electrons are present here. This is second period. 8 electrons are present. Here third period. 3s 3p. Here 2 electrons. Here 6 electrons. So here 8 electrons again. 4s 3d 4p. 2 plus 10 plus 6. D orbital can accommodate maximum 10 electrons. That you have to remember. See here how many? 18. Here also 18 electrons. Here 6s, 4f, 5d, 6p. That means how many? Here 2 plus 14 plus 10 plus 6. Total how many electrons? 32 electrons. Here also there is a chance for same 4 orbitals are there similar to 6th period. 32 electrons are present. This number of electrons. So because of this number of electrons particularly present in period, we can say this is first period is shortest period. This is the shortest period. This is these two are short periods. Short periods. But this is first short period. This is second short period. And these two are long periods. Long periods in the periodic table. This is first long period. This is second long period. Here these two are now. Because earlier all elements are not discovered, but almost all elements are discovered now up to 118. So here before that we are considering this sixth period as longest period. Longest period, but nowadays I think this is not exact because all elements are discovered in even seventh period means it is also long, like sixth period, because of here also 32 electrons, here also 32 electrons. Earlier in seventh period all elements are not discovered, less than 32 elements are there. So that we are considering this seventh period as incomplete period. Incomplete period, but this is longest as per earlier concepts. This is incomplete. This is incomplete because all 32 electrons are not present. Incomplete period as per earlier concept, not now. As per me now, these two are longest periods only compared to this. This is a long period means these two are longest. Longest period as per earlier concept. This is longest, this is incomplete. But nowadays we can say these two are longest periods because all elements are now discovered. Okay, up to this you have to remember in this session. In next session, by using this concept, again I will write in next session these things. In next session, by using this, how to draw total periodic table, we'll discuss. Okay, up to that, stay home, stay safe. Thank you.